Yeah. So great. So Dr. Naeem is with Baker Hughes, right? And it's quite interesting because his degrees, by the way, both of them, the master's as well as the PhD, are from Imperial, right? So this is really exciting. And he has a master's in aerospace, and the second one is advanced structure ceramics, if I'm not mistaken. Yeah.
Yep.
Yeah. Okay. Yeah. He also has a degree from the international development from the London School of Business. He did his postdoc in KAUST. Yeah. And I think since 2014 he is with Baker Hughes, where he is leading, all the efforts with respect to additive manufacturing. It's a really hot topic, and I'm really excited that you're here today and you will be speaking to us. Thank you so much.
My pleasure. Thank you so much, Dr. Glatz. It's always very exciting to speak and interact with the students, because I expect them to be a very engaged audience, and this is what I expect from today's talk as well. So without further ado, we are already a few minutes late, and my apologies for not being able to work out the Zoom. We have some technical issues. So let's start. So the topic is challenges and opportunities of additive manufacturing technology. The way I'm going to describe this is there are challenges and opportunities with how the technology, whether the technology can make a difference to some of the challenges that we have today in the world. And then also there are challenges within the technology itself, and we still need to develop it in some areas to really, allow it to make a difference and live up to its promise. So, talking to an audience in a university, I think both of these aspects are important, but I think the more important one is perhaps the second aspect. Where are the challenges in the technology? Because I believe I'm talking to the technology developers and researchers here. So I'll try and cover both aspects. So basically giving you what is the reward at the end of our committed journey in making additive manufacturing more feasible and solve some of the challenges that technology is facing today in the shape of solving some of the world challenges. So let's start off with the world challenges then. So I have listed down 4 top ones. So, there's no particular ranking. It's based on what I came up with. Obviously, we can't promise to solve world hunger and anything else, big words, but at least some things that we can talk about. So environment is at the top of the list. Then the need for mass customization. Then there's also the idea that we need more complexity because some of our problems are complex, and then quick and on demand is what we need, from movies to content online. Everything is becoming on demand now. I don't remember last time when I actually watched a TV show when it was actually happening live. It is always after when it's done and in our own leisure time. So that's one analogy that I would like to draw. So environment. So what is the challenge today with some of the challenges? So first one, talking about the manufacturing. So the process of manufacturing itself is quite inefficient. Whichever process we talk about, energy consuming, there's a lot of wastage. So there are inefficiencies that can be tackled. The second one is transportation. Right now, manufacturing, they're kind of manufacturing hubs. So parts are produced or equipment is manufactured in certain parts of the world or in certain places, and then it gets shipped around or put on an aeroplane and taken to another part of the world where it actually will be deployed. And that obviously leads to long supply chains. And now we have learned a lot what those long supply chains, how can they be hurt in a situation like COVID, where there is there are travel restrictions, and there are risks involved in moving people and equipment from one place to another. So there we already see the kind of impact that these long supply chains face. Then the mass customization. So this is more to do with the biomedical application, but nonetheless in other places as well, in other sectors as well, everybody is slightly different and unique. So if we talk about hip replacement and joint replacements and other organs, and everyone is slightly different. So customization right now is super costly and expensive if we use the traditional method. Can additive help in that? Then complexity, I already mentioned, we face some really complex problems, and we need complexity to tackle maybe other issues that I've listed here, environment to mass customization to a lot of other issues that complexity can solve. Complexity means that we have now, say, additional tools in our hands to tackle some of those problems. Then quick and on demand. So this is to do with inventories and the lead time. Again, it reduces some of the process inefficiencies. So inventories is a big deal. Companies have huge inventories, both in terms of the size and also the money. And so we would like to reduce them. Why would we keep such a huge warehouse full of parts which probably will never be used at some point and thrown away or written off? And reducing the lead time has a direct impact on the non-productive time. So imagine if there is an asset down, and it, just because there's a missing part and it takes, let's say, 6 months to get it. Now for 6 months, that machine will be out of service. So at some point, it actually affects the consumers because things become more expensive to produce, hence they become more expensive to buy. But can additive help us with some of these challenges? So this is where we will go through a lot of questions and see whether we actually get to an answer. Manufacturing is nothing new. We started making things from Stone Age, so there's nothing new there. Went through the Bronze Age and then the Iron Age. What is different now? Why additive manufacturing is different from whatever we have done before? Well, the big difference is we are completely changing the way we used to make things. Before that, let's say this piece of rock that I have there, it started off as maybe slightly bigger piece or maybe close to this shape. Then the rest of the material around it was chiseled away or somehow broken away, and then we were left with a tool. And nothing much has changed over the last, let's say, for a few million years in this arena. So either we learn to melt this material, melt these metals, and put them in a mold to create, or manage to push them through a certain mold to get them into a shape. Now that is all what we call subtractive manufacturing. You subtract the material away. Now additive is exact opposite of that. In additive, we add material, that's the word additive, where we need it to be to come up with a shape at the end. So most of the time we start off with either a powder or some kind of a melted material that gets deposited in certain locations and then either cured, or if it's melted, it just solidifies. So that's the difference between additive and the rest of other manufacturing techniques. But why does it matter? What's the big advantage of it? So here I have got some definitions. It's more for the academic reasons that I've put them there. But I've already explained how additive actually works. It's just adding material together and either layer by layer. This is usually how the process is defined by a few international bodies like Waller Associates or TWI. So this is for academic reasons, but I hope you got the concept of how additive it actually works. It starts off with a CAD model, so you have a digital file, then you're converting into a solid part layer by layer. So that's essentially the process. And these definitions, very similar, they almost say the same thing that I've just mentioned. There are various ways to various modalities. I've listed 7 of them here, and they're all called additive manufacturing. So it's not one thing. It's generally whatever fits in that definition could be considered as additive. So powder bed fusion, and I've listed down some of the materials that can be used in these modalities to make parts. So powder bed fusion is quite versatile. You can go from polymers, composites, metals, and ceramics. Direct energy deposition at the moment is mainly the metals. Stereolithography is polymers, composites, and ceramics. So metals are not there yet. Material extrusion, polymers and metals. Binder jetting is versatile, so it's pretty much covers all 4 different types of materials. Materials jetting is polymers, metals, and composites. So ceramics are a bit difficult there. And sheet lamination is again metals and polymers. So there are a lot of detail that I can go into, but I'll focus more on maybe powder bed fusion and direct energy deposition. The others are also similar in nature. So just for the purpose of explaining, so powder bed fusion is we start off with powder and we deposit a layer of this metal powder, which is then melted using laser, and wherever we need this part to be to create that shape. So it's a layer by layer process. When one layer is completed, then it is actually on a platform, and the platform moves down a little bit, and then the next layer of powder is deposited. Obviously, the thickness of the layers and the laser energy and etc., and the particles, they are all important factors that needs to be considered when we are setting up this process. But the process repeats itself until the part height is reached, and now it is sitting in a powder bed. So that's where the word powder bed comes from. And then the rest of the powder is taken away, removed, and then we are left with a part sitting on this platform that we can either break off or cut it off this platform, and then either do some post-processing, or if it's good enough to use the way it is, then that's what we do. Direct energy deposition is where, rather than having a powder bed, we start and layer is deposited. Basically, there's a nozzle, and the powder comes out of that nozzle. The location where we want to melt it, where there's a laser pointing at the exact same spot, and then that's where the powder melts, and the part is kind of grown like that. So the rest of the techniques are very similar, either sheet lamination or binder jet. It's just a different way of putting things together. Either we are kind of gluing them together in some cases, or using polymerization, or layering, depositing a layer coming out of a nozzle. It's kind of melted, so it sticks to the layers underneath it, or we put sheets and then kind of put them together. So that's but the process is very similar in nature, maybe different material and slightly different way of putting it together. Now let's start to look at some of the challenges. So environment was the first challenge that I mentioned. So it's an inefficient manufacturing process. Transportation and long supply chains were the issues. Additive has quite a high yield. So tackling the first part, inefficient manufacturing process, most of the material, most of the metal powder or the material that we use ends up as a part. And the yield is quite high, and then the rest of the material, let's say whatever is remaining in that powder bed, if I take that as an example, it goes back into the store, and then we can reuse it again. That's one. Secondly, since it's not a very heavy, let's say, we don't need too many people to print a part. The process has the potential to be completely automated. So what we call lights off, doors shut manufacturing. So, if there's enough powder stored that that can be fed into the machine, someone can remotely operate the machine, and then no need for any supervision. It will just continue to operate and print the part. To the point that that future is not far away right now, but it could be possible that the printer actually takes orders directly and then trying to schedule them and starts printing. It is actually possible, but again, I will get to the challenges that are associated with additive right now, some of the limitations that we yet to overcome. And the third one is the supply chain and transportation issue. We don't need a big factory, let's say, to make a part. It's just you have a machine, some post-processing equipment, and that's it. You're good to go. In some cases, all you need is a machine, and then you can print a part. That means we can make a manufacture close to the point of use. Now, this was very handy in COVID times because of this disruptions and lockdowns, and all these you can say face shields and some of this medical equipment started to be produced locally. So Baker Hughes played quite a role in that, because we have our global capabilities sitting in different regions. So not just us, but anybody, even people with just a desktop size 3D printer, plastic 3D printer, could produce face shields and supply them to hospitals, whatever anybody could do in these testing times. But again, the point is that we have seen the benefits of that already in these testing times. So, there is some of these challenges can be addressed by additive. Now we will see how effective it is, where we are in this journey, on where we say, yes, it's done already, not 100% done yet, but at least the potential is there. Now the next one is the mass customization. Biomedical applications I mentioned before. So it has mass customization potential. Every part could be unique. And since we don't need a mold or anything, it's a CAD file, it's a digital file, we can modify it. We can make small changes and adjustments. And customization is possible with pretty much all the technologies, but the main issue is the cost. For example, if we are casting parts, then you need to create a mold, and every time you have a slightly different shape, you can't go back and create another mold with that shape. It takes too much time and takes too much money, makes it more expensive. Here, the cost of customization is almost nothing. We just need to modify the CAD file, and we will get a part which is customized for that particular application. Let's say for a particular patient, if we're talking about, let's say, hip replacement. And every part can be unique. And this is something which is already there. I don't think there's too much in this challenge when it comes to additive manufacturing. The next one is complexity. As I mentioned, the problems are complex and requires complex solutions. So if there's one thing that I want you guys to remember, that is complexity is free in additive manufacturing. Usually with the traditional manufacturing methods, the cost of manufacturing goes up with the degree of complexity. As you can see from the curve here with the conventional manufacturing, the more complex the part gets, the more expensive it gets. With additive, it's pretty much flat line. We can make some seriously complex shapes, which are probably even impossible using traditional methods. And let's say if I give you an example, let's say if I want to print a cylinder, that's a 3 inches tall cylinder, simple cylinder, 3 inches tall. Or if I want to print a mesh, which is, let's say, same height, 3 inches tall. The cost of mesh is probably less than the simple cylinder, because it will take a little less material to print with. But that doesn't mean that the cylinder will be cheap in additive. But that mesh probably we won't be able to produce it even at 3 times the cost using traditional methods. So if I talk about the most expensive part that we can print right now, it is probably a cube of the size of the build area, build volume, is the most expensive part we can print. But as I said, the complexity is free, but that means the simpler parts become more expensive and the complex parts becomes cheap in additive. So that's where we should, when we are selecting parts for appropriate for additive manufacturing, we should look at how complex they are, because that will determine whether additive actually makes sense or not. Quick and on demand, reduce inventories and reduce lead time. It's all digital. no molds required, I mentioned before, and it's quite a quick manufacturing process. In the last, and it's still getting quicker and quicker. So now we can produce parts within a matter of hours, which is probably not possible with any other way. It's getting quicker and quicker. If I talk about last 5 years, the manufacturing process has become, I would say, around 12 times faster than what it was 5 years ago. That is to do with people using, let's say if I talk about powder bed fusion, people using multiple lasers now. Machine manufacturers are coming up with machines with like up to 8 lasers, or even that talks about 12 lasers. And then the layer thicknesses are getting bigger and bigger. So, it's getting faster and faster. And then the next thing is we can qualify parts in advance, keep them as a digital file rather than a physical part, and print when needed on demand. Again, so the concept of digital inventory is not an alien or, let's say, far-fetched in the future anymore. It's being done right now. Now, supply chain issues. So we talked about it before, and I have briefly touched on it. It's not that anything that we can print should be printed. As I said, pretty much anything, most of the complex geometries can be printed, but it doesn't mean it should be. It should be the right product, right quantity, under right conditions, at the right place, at the right time, at the right cost. So it's not like we have a hammer. Let's say if I buy a hammer, I won't go fixing all my problems in the house using a hammer. It has its place. Same with additive manufacturing. It's not like we should apply it everywhere. It has its place. So there are question marks whenever there is a part that needs to be printed. Do we really want to print it? Does it actually make sense to do it? We have already mentioned some benefits. So if I want to characterize them into 3 categories, so relieve, improve, and grow. So emergencies, as I said, it's a quick process. You can reduce the cost, you can reduce the lead time. If it's difficult to manufacture, if it's a long time for a product to be developed, because remember, it's a quick turnaround. We can print a part, quickly turn around, see if there's a problem with it, print it again. These iterative process of let's say improvement process can be very, very quick. So we can increase the time, reduce the time to market. Improve, we can make parts more reliable. Because remember, we can make things complex. That means we can consolidate parts. If it was something which was made of 10 parts or 12 parts, no need to do it that way anymore. Make it as one. Even repairs, we can repair parts. Let's say something is broken, we can just rebuild it. Reduce the inventories. As I mentioned before, digital, and we can reduce the life cycle cost of the part. Maybe the part is more expensive on its own, but if you look at the whole life cycle, it's become cheaper. Improve performance, form, fit, function. As I mentioned, so we can print many parts, assemblies into one part. So we can eliminate the assemblies. And we can optimize even the material properties. So we will touch on those. So there's a concept of generative design, digital inventory, which I've just briefly mentioned, but I'll get back to this in the next few slides. So just hang in there with me. How AM is impacting? I've mentioned before there are issues and there are solutions that can be solved, but how much of this is real right now? Look at some of these industries, biomedical, then we talk about aviation. There are some examples here, automotive, even drones. So biomedical was one of the first industries to adopt additive manufacturing. Right now, they are one of the biggest, I would say, benefiters of it. So there's a hip implant, which is additively produced. Department of Defense in the US is 3D printing autonomous drones. GE Aviation is a big benefiter. They are one of the most advanced right now in the aviation industry when it comes to additive. And they've printed some really complex parts, some really high demanding application parts. So now when people talk about how reliable additive is, now I don't have to mention anything else other than that you have already probably flown an airplane that had critical parts made using additive. So you have unintentionally already trusted additive with your life. So it's proven that these parts can be reliable. So there's no issue there. But obviously there's a process that needs to be followed. So there are all of these different industries. NASA, majority of rocket engine parts are made of additive. Right now, we want additive Baker Hughes is printing parts for NASA from our US facility. So it's impacting already, big time. Now let's talk about some of the problems we have. So I put a big rosy picture of what we can what can be done. But now let's see how the process works and where are some of these limitations that needs to be overcome. So this is where you guys need to start working on some of these and help us, help the world. It starts off with a demand signal. It could be a new product or some kind of a reproduction of an old part or some redesign. So you start off with that, then we get to the design or reverse engineer. Now the word reverse engineer is here, and we'll discuss it a little bit briefly on what that is and how is that challenging. Then it gets to printing the actual. You have a CAD file now through our design or reverse engineer, and we need to now make a part out of it. So that's the process of printing. Rarely is the case that the part can simply be taken out of the printer and used, so there's post-processing required. And once it's completed, then we go through a qualification and acceptance to make sure it meets all the requirements. Now, this is the promise. Promise is demand signal is predictive and automated. We don't want to be in a position where something fails and so, oh my God, now we need to fix it. It should be, we can either predict that there will be a failure and then automated ordering where demand signal automatically goes. Let's say, but the idea of digital twins comes in. So a part is about to fail, some sensor detects the problems, and then a demand signal automatically is sent to the printer nearby, and it prints the part. That's the promise. Design, it should solve the problem first of all, and now that's where additive has an advantage, because now the traditional manufacturing methods have limitations on what can be manufactured. So the designer's mindset is, I need to figure out whatever I'm designing, I'm able to print it. I'm able to manufacture it. With additive, now I would say the design space has become bigger. It's not infinite, but it's considerably bigger than before. That means it's a little less of a worry for the designer on how this design will be created into a shape, but more of a, will it actually solve the problem that I'm trying to solve? Inconceivable products. So inconceivable product means stuff that we can't imagine right now. Then it should be automated. Can we automate the designing process? Promises there that we can make some really complex shapes to solve a problem, and we can automate that process. Printing, the promise is quick, cheap, close to point of use, reproducible, and flexible. All of these is a promise. Post-processing, we wouldn't want to have it. Right now, the numbers are around 70% of the cost of an additive part is the cost of post-processing. It has severe limitations because we can produce something really complex, but if it requires, let's say, some post-processing or some surface finishing, then we will have to put it as a limitation. Then we can't really go and fulfill that promise of really complex parts. So we would like to eliminate that. Then finally, the acceptance and qualification should be quick, reliable, and traceable. We should be able to trace back anything that we have done to that part. Now, when we are getting to the solutions and where we are, my request is don't look at additive in isolation. It is part of 4IR ecosystem, and there's only certain things that additive can do on its own. And the rest of these 4IR technologies are what we call tech multipliers. So additive on its own can do certain things, but imagine if we start to use computers to design parts. But the idea is, the generative design, or we start to use AI and machine learning to predict failures. I mentioned before automated predictive demand signal. And if we could start simulations before we actually print, so make it more reliable and improve our success rate of how many parts we can print which are good enough in the first attempt. So don't look at it in isolation. It's part of a much bigger ecosystem. So most of these technologies, in some shape or form, they will come into this picture. Now, demand signal. Promises, predictive and automated. What is the state of affairs now? Right now is reactive. Action is only taken when issues arise or failures occur. So the idea of prediction is not there yet. It's not an additive limitation, but it is where things need to be connected together. Selection of right tools for the right job. So generally awareness and there's misunderstanding about additive. As I mentioned before, it's a hammer, but we can't fix every problem with it. Supply chain, so inefficient ordering process. Right now, if let's say there's a failure and we want to place an order for a part, it will take maybe weeks to get an order through, because there's a lengthy chain of approval processes that they are built into the system. So that system needs to be changed, because otherwise we can print a part in a few days, but if it takes us a month to get to that point, then that month is still wasted. So somehow we need to figure out how to go around that problem. And it's manual and slow. So obviously there are these issues that needs to be addressed before we get to this predictive and automated promise to be delivered. Next one is design. Okay, I've put whatever is possible in green, right? So solves a problem that's built in additive. That's the biggest advantage we have, that we can have really complex parts. So that means that design space is bigger. Inconceivable products. Now, where is these coming from? Well, designers' mindset needs to be changed. Right now, we have trained more designers within last year, 2 years for additive than for anything else. And that is because they're still thinking in traditional manufacturing way. So that's a mindset change that needs to go through. Customer mindset needs to be changed as well. So they want to replace parts with the exact same material and design. Obviously, that design was created because of the limitations that were there in the beginning, when originally that part was manufactured. Now we need to think of how can we make it better. So there's the mindset, it's working, I want to keep it that way. Actually, we can make it way better. So, let us open up and think about it that way. Then availability of tools. Traditional design tools work to some extent, but there's more simulation, additive process simulation that are being developed. So there's some development work being done. It's going very, very rapidly. So people like ANSYS and NX and Autodesk, these guys, they're doing a phenomenal job of really pushing the limits, but still there's a lot more needs to be done. Now the last part is the most important one, generative design and topology optimization. I actually touched on it before. It's in their infancy right now, but that's where all this inconceivable products and automation will come into picture. Inconceivable products, we can still design them using traditional methods, but it's a painstaking process, because the way we think as humans, we have evolved to see things and try and then imitate them. So that's why aeroplanes looks like a bird, because at that time the only thing that we saw flying nicely was a bird, so it looks like a bird. That doesn't mean it's the only shape that can fly. Same applies on everything else we do. Computers don't have that problem though. They can, if they are given the right constraints, they can design a part, come up with a design specific to solve that problem. But that still needs to be developed. Those tools needs to be developed still. The promise is there, and we are getting there, but I think we are still maybe a year, 2 years off to get anywhere near there. So their automated is still a promise, and it will take some time before we deliver it. Now, reverse engineering. Now, that's a complex one. Flexible, so we can recreate two things, right? One is the recreation of the surface geometry, and the second one is internal structures. Surface geometry, where we have various types of scanners now, and we can are available, and we can scan the parts and get a CAD file. But internal structures are a bit more complicated. X-rays and CT scanners and ultrasound, they can only get to a certain depth into the material, and it's so there's a limited capability there. One big thing is IP issues. If anybody can get hold of a scanner and the right equipment, they can take anybody's part, scan it, recreate it. Now, obviously, we have all the IP protections and patents and everything, but it doesn't always work, because if the technology keeps getting better and better, and then there are people out there who really don't care about IP, they want to get on with it, or in some cases, there's no way to protect it. Especially, let's talk about defense industry. I don't think many people will care if there are, foes. They would say, well, we will get it. Nothing stops it. But that's where it becomes a risky business. We need to be careful. Quick, yes, it is quick. Now, at the moment, go to TAP, and these guys have a scanner. It takes a few minutes to scan a part, so it is quick. But the other issues, automation is not there yet, to some extent, and captures all aspects, not yet. Internal structures are still a problem. But there's work that needs to be done. It's going on, but still more needs to be done. Printing. Now, there's a long list here. Limited choice of materials available for 3D printing at the moment. So if I talk about materials and printers, the choice of materials is limited because we need a high quality powder, and it's relatively expensive to get. Changing the material in the machines, it's getting better. I was in Germany last year in the Formnext conference, and I saw printers where they were claiming that you can change the material within, let's say, 30 minutes. Not proven yet, because cleaning methods that really make sure we have no particles left of the previous material are not there. So that there's more work to be done on that. Machines qualified for specific materials, so reproducibility is still not 100% there. I can print a part on one machine, but if I change it to another manufacturer, might have to still go through the qualification process, which is expensive and time-consuming. I mentioned before, customers want to use the same material on the replacement parts. Usually when we get the requests like these, question is why? Oh, just because it's made that way before. Well, it was made that way because the material was expensive, and if you had made a part made of another expensive material, the cost would have been high. Here, the cost of material is slightly expensive, but really the part of the cost that the material has in the whole cost of the part is actually relatively small. Most of it is to do with either post-processing or mainly to do with how much time it takes for the printer to print it. So quick customization close to point of use is fine. Cheap is still not. Reproducibility still issues. Flexibility, if I could print a part on any printer without going to big process, then it will be quick. Printers, reproducibility, as I mentioned before, there's a lot that needs to be done in situ process monitoring. There's a lot that is being done right now because printer manufacturers understand this. And the size limitation. How big a part can I print? There are different technologies that can go to different scales, but we still need to get much better at it. And we still need to be able to print a big part in short time. So that limitation needs to be overcome still. Being done is work in progress. So, with maybe a few years and we will get there. Post-processing, we don't want any, as I mentioned before. So heat treatment, surface relieving, surface finishing is time consuming. You need a large footprint. So the idea that we can localize the manufacturing point close to the point of use, we need to get rid of this. So I'm glad we are working with KFUPM. We're starting work on some of these limitations with the KFUPM. So heat treatment is one, for example, and then a few others that I touched before. But this is another challenge that we need to overcome. I think this will take a little while, and I don't think it will go away 100%, but I think we can do much better. Qualification and acceptance. Quick, reliable, traceable. At the moment, there is industry accepted standards that are being developed. Technology is growing much faster than the standards that needs to be there. So there is this big debate now on how do we fix this, how do we go through this process quickly, but obviously we need to be careful not to rush things, because the best way to kill any new technology is to rush it through and produce parts which are not good enough and then just kill it there and then. The main difference though in previously accepted standards and additive is the melting methodology. That's the main difference. That's where the effort needs to be. How do we standardize this process? How do we make sure that we always get it the same way? Now that's where the problem is, and that's where the more effort needs to be. Monitoring. So this is where additive actually is much better, because we can really, you can say, look at the defects as they are forming during the process. So that's where it's probably even better than traditional manufacturing methods. Every layer, every micron on that layer can be and is being scanned for defects as we are printing. So this is where it's probably way ahead of other manufacturing methodologies. Mindset, fear of the unknown, conservative approach, and the lack of full understanding of the process. I think that's where acceptance and is suffering a little bit. Standards, I talked about standard before, but here I've listed a few. So from terminologies to design, material, methods, health and safety, quality, they're all being developed. Some of them are there, but they're all being, and some of them are being developed at the moment. So the work is underway because everybody sees the potential. So there's a lot of effort going on in that front. I have mentioned here something about material properties that we can get out. So we can see different methods of manufacturing, including additive there. And in terms of the properties, it does get pretty close. In some cases better in some properties, but it does get pretty close. So in terms of the material properties of what we can get is up there between casting and forging. Let's say that's where it is in most of the cases. So I've talked about stainless steel. Here is nickel 718. Some of the properties of nickel 718 and compared against casting and forging. So you can see it's not far off. In some cases, it's even better. And this is Ti-64. So these are three key materials. That's why I put these three as example. The Ti-64 has a lot of biomedical applications as well as aerospace applications. Inconel 718 or nickel 718 is high corrosion resistant, and so it has a lot of applications in various industries. And steel is of course the main material used everywhere. And so these are three main materials, and you see in terms of the properties they are not bad, they're comparable. So missing links, this is a summary slide of what we talked about. Predictive and automated, so there's a failure prediction using AI that needs to be done. Design, so we need generative design softwares, customer mindset, IP issues. Cheap, reproducible, and flexible printing. We need more robust printers. In-situ process monitoring need to get better, make it easier to change the material, and offer a whole solution. Means don't get us into the post-processing. And obviously we don't want any post-processing. And for the last one, more effort required from industry-wide. It can't be one company, it has to be an industry-wide effort, a global effort to develop more standards. Change of mindset, again, will come with time, but I think we can do more to change that, especially the young graduates and the young guys like you who will join the industries. I think it's important that you guys are aware of this so you can make the most of it. Internal standards development is another way forward. Most of the companies, including us, we have developed our own internal standards, and they are pretty good because we have produced close to 50,000 parts in the last few years. with zero failures so far, because we have developed internal standards. But global effort is still required, and everybody needs to catch up to that. That's how it should really be. Now the old days are gone where everybody works in their own little bubble. So from demand signal, everything else should work around that. From post-processing, printing, reverse engineering, and qualification, everybody need to work together. We can't have these different teams now. It has to be one team where all these expertise sit. And this is how things are actually working. Wherever we see additive manufacturing as a success story, the teams are multidisciplinary. Oil and gas industry, I'm talking to KFUPM, so there should be oil and gas in there. So I'm not going to miss out on that. We are sitting in a country which supplies most of the hydrocarbons to the world. Oil and gas industry has challenges with a lot of old equipment, part failures, and long lead times with expensive consequences, because we have rigs far away. If one part fails, the cost of an hour is really high. We're talking about $100,000 in some cases. Large inventories, very long supply chains, as I mentioned before, go far in empty quarter, sitting in one corner, and then another side is somewhere in the middle of an ocean. And long-standing problems, either solutions don't exist or they are very inefficient. And we are notorious for having a very big carbon footprint. Additive can solve quite a few of these. So here, additive service, inventory management, we can, that's where we can solve some of those issues with the large inventories. Then emergency service, scan, reverse engineer, 3D print, we can reduce the lead time. Point of use manufacturing solves the problem of long supply chains again, and reduces the carbon footprint big time. Engineering and generative design. So this is where all those long-standing issues can be solved, which have been with us for a while. So, just put it one slide here because I didn't want to be too general in my discussions, but specific to oil and gas, there is a lot of promise, and it is being adopted quite quickly globally. Concluding remarks. So here, what I've just mentioned before, obsolete parts is quick manufacturing, inventories could be digital, point of use, complex parts can be manufactured and reduce the carbon footprint by reducing the supply chain. There are some problems that need to be, some challenges that need to be resolved, but overall, for oil and gas industry, there's a lot that we can do today. The dream, we have printer on site, part prediction of the failure, automated scanning, signal to the printer, print the part, and deliver on time. So no lag times, all of those issues resolved. That's the dream, but we have already discussed what needs to be done to make this dream come true. World challenges, we talked about them in the beginning, where we are now. So again, it's a summary slide that we discussed before. So environmental challenges, high yield, print close to the point of use, and we reduce this transportation and long supply chain issues where we are consuming a lot of these hydrocarbons and making this planet not that great for the future. Mass customization, so with additive manufacturing, no additional cost for customization. Complexity is free. Remember, that's the key for additive. And design for additive, because we need a way to make complex parts. Quick on demand, reduce inventories, convert your physical inventories into digital ones, and reduce the lead time of obsolete parts by making the process quick. It's a very quick manufacturing process. That's it from my end. Sorry, I think I took a little longer. I wanted to make it short, but for a question answer session, I think we still have a few minutes. So anybody with any questions?
Yes, actually, I already received questions through the chat window from one of our students. And if you would be so kind, so his mic is not working, if I can ask you on his behalf. So one question that was, it's Muhammad Malik, by the way, and he's asking, what is the minimum maximum size limit for 3D printing?
Good question. So it depends on which technology, which modality we are talking about. I can give you information about, let's say, as an example, powder bed fusion technology. Right now, we can go, the biggest printer we have is 800 millimeter by 800 millimeter by 800 millimeter. So 800 millimeter cube, which is 0.8 meter in all directions.
Okay.
So that's what was unveiled, I think, a couple of days back.
Okay, thank you. The second question that came up, so he's asking with respect to prop ends, and the question is there currently material like, you know, like prop ends, it's usually sand, some quartz, or maybe some ceramics. Is this possible? Would it be possible to print this?
Ceramics?
It's very small,
yes.
yeah, ceramics or quartz.
Ceramics can be printed. And we are currently doing that with in our center in Houston. Ceramics can be printed. It's a different print. I mean, I've mentioned a few different printing modalities, and you know, ceramic is listed in a few of them already. So it's possible to print, yes.
Okay, so I think what he's hinting at, right? Would it be possible to print prop ends? You know, is this something that would be economically feasible? You know, what would it take to print a ton of small-sized grains? Do you think this would be an option using 3D printing?
I mean, the thing is, as I mentioned before, so is it really, I mean, what's the advantage if we start to print these? There are many other methods to, you know, to make these prop ends. Potentially we can do it, but it will be cost prohibitive. It's so that would be my answer. It can be done, but it will be super expensive.
Okay, thanks a lot. So Muhammad, I hope I captured the essence of your question and you received satisfying answers. Would it be possible that if he has more questions, you know, that I can provide him your email address? Would this be agreeable?
Sure.
To you? Okay.
Sure,
great.
absolutely,
thanks,
no
thanks
problem.
A lot. Thanks a lot. Well, now we are right on time. Thanks a lot, Naeem, you know, for filling us in on this one, and was a pleasure having you. Thanks a lot, everybody.
My pleasure. Thank you so much. Thank you.